proving languages are regular or not regular. This means how to prove that a given language is regular or not regular. This presentation will focus more on proving that a language is not regular than on proving that it is. So let's begin. Closure properties can be used to prove that a language is regular. We can do that by proving that a new language is a result of an operation on two known regular languages. These operations are concatenation, union, intersection, closure, that means concatenating a language with itself, complement, and difference. For instance, we know that given the alphabet CAT, the language that contains strings that contain cat is a regular language. Using I can state that the language that contains strings that do not contain cat as a substring is also a regular language. This is the only example that I will give in this talk about using closure properties to prove that a language is regular. This theorem, called the pumping theorem, can be used to prove that a language is not regular. Why do I use it to prove that? Because the theorem states this. If L is a regular language, an infinite regular language, over an alphabet sigma, then there are strings alpha, beta, and rho over sigma with beta non-empty, such that for any n, I can build the string concatenating alpha, beta, any number of times, 0, 1, 2, 3, any number of times with rho, and the result will be a member of L. Notice it says, if L is an infinite language, which is regular, then there are strings. So if I've proved that there are strings, I haven't proven that the language is regular. However, if I prove that I cannot find those strings, then I have proven, using the contrapositive, that the language is not regular. Usually these proofs are done by a proof by contradiction. I'm going to assume that the language is regular, and I prove that there's some problem that I cannot find these strings, or that there's an n that won't work, and things like that. Let me show you an example. Let's say I have the alphabet that only contains A, and let's say L is the language of strings of A such that their length is prime. So I would have, L would contain a word with 2 A's, a string with 3 A's, a string with 11 A's, and all of the prime numbers. This language is infinite because there is an infinite number of primes. Let's assume L is regular. Then by the pumping theorem, there must be strings alpha from A star, beta, strings of A's, and rho, also strings of A's with beta different from lambda, such that for any n, alpha, beta, concatenated with itself 0 or more times rho is always a member of L. Since alpha, beta, and rho are strings of A's, I can define them as alpha as PA's, beta as QA's, rho as RA's. Since beta is not lambda, then I know that Q has to be greater than or equal to 1. If alpha concatenated with B n or n times with rho is a member of L, that means that P plus n times Q plus R is prime for any n. Let's say that n is equal to P plus 2Q plus R plus 2. Clearly, n is greater than or equal to 0 because all of those values are greater than or equal to 0. In fact, Q is greater than or equal to 1. So in fact, this number is greater than or equal to 4. Okay, let's start P plus NQ plus R. Let's replace P plus 2Q plus R plus 2 for N. I just replace it. Now I distribute Q over that sum there, I I do the math, and then it's p plus pq plus 2q squared plus rq plus 2q plus r. Now I'm going to divide that into two factors, which is q plus 1 times p plus 2q plus r. Notice that these two values, if q is greater than or equal to 1, if q is greater than 0, it's because it's greater than or equal to 1. It means that q plus 1 is greater than or equal to q. 2q would be greater than or equal to 2 as well. That means this number is greater than or equal to 2. This number is greater than or equal to 2. This means that this number, using n equals p plus 2q plus r plus 2, is not prime. It's composite because it is the product of two numbers that are greater than or equal to 2. This is not a prime number because q plus 1 is greater than or equal. Q plus 1 is greater than 1. That means it's greater than or equal to 2. And p plus 2q plus r is also greater than 1, strictly greater than 1. Then this is a composite number. We found an m for which the statement does not hold. This is a contradiction because it says for every n, this should be prime. Therefore, I arrived at a contradiction, and my only assumption was that L is regular. Therefore, L is not regular. The problem with the pumping theorem is that here I had to notice that alpha, beta, and rho were arbitrary strings of A's and B's. I didn't assume anything about alpha, beta, and rho. Since they could only be formed with A's, it was easy. If the alphabet contained more symbols, then I would have to take into account all of the possibilities that I had A's mixed up with B's and things like that, and maybe I would have to take into account many more cases. Fortunately, we have something called the pumping lemma, which I will talk about on the next slide, on this slide. The pumping lemma states the following: let L be an infinite regular language over sigma. Then there is a constant k which depends on L, such that for any omega in L that has more which length is greater than or equal to k, there are strings alpha, beta, and rho in sigma, such that rho is equal to alpha, beta, rho. You see, I'm dividing omega, whose length is greater than or equal to k, into three strings, such that the first two, when I concatenate them, their length is less than or equal to k. I also say that beta is not lambda, and the theorem says that for any n, if I've chosen the substrings in that fashion, alpha, beta, pumping it n or more times rho, should always be a member of L for all n's greater than or equal to 0. That constant k is the number of states in the smallest finite state automaton that recognizes L. But we don't really care what k is. We just know that k depends on the language. So we have that. And again, we cannot use this lemma to prove that a language is regular. Because if L is regular, then those strings exist. If I show that those strings exist, it doesn't mean that L is regular. However, if I show that I cannot find those strings, then the language is not regular. And that's what we will do in the next two examples. Okay, we will show the use of the pumping lemma to prove that this language, a sequence of m a's followed by a sequence of m b's, is not regular, the same number of a's and b's. Let's suppose that L is regular. By the pumping lemma, there is a constant k such that for any omega in L longer than k, there are strings alpha, beta, and rho such that omega is equal to alpha, beta, rho, and such that the first part, alpha, beta, is less than k. The length of that part is less than k. Beta is not lambda, and for any n, alpha, beta, rho, alpha, beta, beta rho, or just alpha rho if n is 0. And for any n, that means alpha, beta, n, that means concatenating b, beta to itself n or more times, then that should also be a member of L. If I find any n greater than or equal to 0 for which this doesn't hold, then the language will not be regular. Let's show you why. Then I'm going to choose a string. Let's say the string is KAs followed by KBs. That K is the K that is a special K for this language. And clearly omega belongs to L. We must find strings alpha, beta, and rho such that omega is equal to the concatenation of alpha, beta, rho. The length of alpha, beta is less than or equal to K. Beta isn't lambda. And we have that, then we need to show that alpha, beta, repeated some number of times, rho, is not in the language to show that the language is not regular. So let's say I'm going to choose n equals 0. Oh, before that, notice that if the length of alpha and beta is less than or equal to K, and I know that omega has KAs followed by KBs, then if the length of a prefix is less than or equal to K, it means that that prefix may only contain A's. So I can say that alpha is equal to SA's, beta is equal to TA's, and rho will be equal to XA's followed by KB's. And I know that S plus T plus X should be equal to K. And since beta is not empty, is not lambda, then T has to be greater than 0. Clearly, S plus T is greater than K. So then it should hold that S plus NT plus X is equal to K for any n. You don't really have to prove it. You see that the only n that will work is 1. But to have a correct proof, we have to show an n for which it doesn't work. We could choose 2, we could choose 100, but let's choose n equals 0. I have to choose that for every n, S plus NT plus X is equal to K. Then, since I assume that n is 0, then S plus 0 times T plus X is equal to K. S plus X is equal to K. My hypotheses here state S plus T plus X is equal to K. So then I replace S plus T plus X for K. Then I subtract S plus X both sides, and I get that T is equal to 0. However, this contradicts the fact that T is greater than 0. Therefore, we found an n for which the statement does not hold. This is a contradiction, making our assumption false. The only thing I had assumed was that L is regular. Therefore, L is not regular. The next proof, this part will be the same, but it's a different language. Okay, I'm going to show you another example. This example, the last part, will be exactly the same as the previous example. The trick, as always, is how to find the string which I will break up into 3 substrings such that I can pump a part of the prefix of that string which is not empty. So then the language that I will prove that is not regular is the language of the palindromes over AB. That means that language such that the reverse of the string is the same string. So I'm going to assume that it's regular. By the pumping lemma, there's a constant K such that any omega such that its length is greater than or equal to K, there are strings alpha, beta, and rho such that omega is equal to the concatenation of those 3 strings. Omega is equal to alpha, beta, rho, such that the length of the prefix alpha, beta is less than or equal to K, such that beta is not lambda, and such that I can pump beta, or I can just repeat beta as many times as I want, even 0 times, and the result will be in L. Then I'm going to, the string that I'm going to choose is KAs followed by B followed by KAs. Clearly this omega is an L. it's read the reverse of omega will be AKB which is AKB. KAs followed by B followed by KAs. The reverse will be KAs followed by B followed by KAs. We must find strings alpha, beta, rho such that omega is equal to alpha, beta, rho, such that the length of alpha, beta is less than or equal to k, and beta is not lambda. Since the length of alpha, beta is less than or equal to k, then I know that alpha and beta are composed of only a's. So then I know that that alpha I can state that is equal to SA's, beta is TA's, and since there are some A's left over, then I would have XA's followed by B followed by KA's. The condition will be if it is a palindrome will be that S plus NT plus X is equal to K. Now, in the first place here, since alpha, beta, rho, the concatenation is in omega, I know that S plus TX, X plus T plus X is equal to K, with T greater than 0. Then this part is the same as before. Let N equal 0. S plus NT plus X is equal to K. If N is 0, then it's S plus 0T plus X is equal to K. That means that S plus K is equal to S plus X is equal to K. The hypothesis is that K is equal to S plus T plus X. I replace it. Then I subtract S plus X both sides and I get that T is equal to 0. However, I had assumed, T has to be greater than 0. Therefore, my supposition was incorrect, and my only supposition was that L is regular. Therefore, L is not regular. Then the only problem that you face when you're using the pumping lemma is how to choose omega. And that's a problem, and many times it's not as easy as I showed you here. Sometimes it can be harder to choose the correct omega, but then once you choose it correctly and you show that you cannot really pump the first part, any part of the beginning of the string, then you have shown that the language is not regular. Okay, this concludes my presentation. Thank you very much for listening.